Okay, so we're going to be looking at planes again in this video, and another way we can represent planes in this way is the scalar product. So we'll see how this works in a minute. It takes the form R, where R is some effectors to some point, dot n, where n is any normal to the plane, equal to some constant d. Okay, and this constant d is going to depend on which normal we choose. But let's have a look at a little diagram. So say we have a plane. Okay, two-dimensional plane in 3D space, and the plane's going to be from the origin. We can get to the plane again like before. It's on vector r, so that's going to take us to some point P. Now there's a perpendicular distance to the line, and we'll call that distance capital D. Okay. Sorry, it's a distance, not a direction. It's the perpendicular distance. Okay, so that's the shortest distance from the origin to the plane. That's going to take us to some other point. We'll call that C, and we can connect up C and P. Because this is a perpendicular distance, this is clearly a right angled triangle. So if we take a look at this right angled triangle, we've got R here, and this is D. Okay, call this angle theta, and actually this length here, because R is that size, it includes direction. This is the magnitude of R. Okay, next line here. So we want to find D, and by our rules of trigonometry, capital D here is equal to okay, we've got adjacent and hypotenuse, so cos theta is equal to D over R. So D is equal to modulus of R. Alright, and now let's take a look at this dot product here. So R dot n is equal to the modulus of R, the modulus of n, cos theta. But we see here that the modulus of R cos theta is equal to this capital D that gets onto the plane. So R dot n is equal to the modulus of the normal vector multiplied by capital D. And all we do is we call this D mod n of this capital D, which is the shortest distance onto the line. And then we get our scalar equation, scalar dot product equation of the equation of a plane, or of a plane. So you can see this works in a similar way to the other, the vector equation. What this one does is we take a normal, so we've got a normal vector, and this gives us the slant of the plane in essence. And then it depends on our size of normal vector. Note that if we take n hat, which is the unit normal, so note the modulus of n hat is equal to 1, then our little d is going to be equal to this big D here. Say n has modulus 2, all that happens is this line extends up twice as high. The plane's still in the same place, but the line doesn't. What I'm saying is constant if we take it as a distance. So the point being, the normal gives us the tilt of the line, and this constant D gives us in a roundabout way the distance from the perpendicular distance the origin to the plane. So once you get the perpendicular distance and then you know the slant, you've described the whole plane then. Okay, because it could be lines with similar normal vectors that sit just below or above, but then this D figures in place. And similarly, if we take this length D here, we can have different slants. Once we fix those two things, there's only one unique plane we can have. So this equation perfectly describes the plane. You might get asked questions like r dot n is equal to d, and you're asked to find the constant d. Well, what you would be given in these questions is you'd be given the normal, and then you'd also be given a point, and you can just substitute r equal to that point. That point, like all points on the plane, will satisfy this equation. Take the dot product, and that returns d. Okay, so that's it. Next video, we're going to look at the Cartesian equation of a plane, which follows very quickly from this form. If you understood this. If you have any questions, let me know in the comment section below. For now, that is it, and I hope to see you in the next video. Thanks for watching.